All right, so I want to talk about some of the features of the text that you've been reading through. And first, let me talk about this program 1.6a. It's on page 9 and 10. 1.6, 1.6b. This is the final form of a first order, and I can call scalar Euler solver. Now, first order, you'll see later on what first order and scalar means. More general would be higher order, second order, and so on. And scalar means there's not vector. There's just one function. Okay, so let's look at some of the nice features of this program. First of all, it's called as a function. Okay. So what does that mean? That means it can be used within routines. That's a good thing. Right, now, the arguments contain the essential information that's necessary. And this is very adaptable, so these arguments can be used to specify any first-order scalar system. Okay, so they're very adaptable, very general. Similarly, the outputs are the essential outputs. And you'll notice that there's no plot routine within the function. The reason is that in various situations you want different kinds of plots. So no plots. If you want a plot, you're going to want to customize that for your particular application. So that's another good feature. This has the time vector and the actual solution function. Okay. Another good feature about this is that it's modular. Now, what do I mean by modular? I can replace the derivative function. Okay, so what does that mean? Actually, go down here to this statement here. We've never seen this before. This looks kind of weird, and to understand this, you have to look at the context. But this is the same statement that previously was the same as dy equals derivs of y and t, something like that. Okay. Notice that derivs handle was passed as an argument to the function. So when you call the function, you specify derivs handle. What is derivs handle? Derivs handle is the name of the function that contains the derivative. Previously we used derivs, and we have the function derivs here. But notice that the way that this program is called, when this program is called, the name of the derivative routine is specified right here with the at sign. Now, if I wanted some other derivative function, if I wanted deriv2, I could call it at deriv2, and I could define a function deriv2 that gives me the derivative that I want. So I could have a whole stable full of derivative functions that I could use. So that's the advantage of this. Now, whenever you want to use the solver, all you have to do is change the argument list. Now, actually, I was not really familiar with this syntax. It looks very handy. I don't use it very much. But the advantage is that if you use this syntax, you don't need to go into the program and change the derivative name. You just change the derivative name in the argument list. So this is a good program. Please write this and save it as a program in your folder, and also save a derivative function like this. All right, now the next section talks about the next step up. It's called second order systems. Remember I said that previous Euler was for first order. Now we're going to second order. Now many of the equations of physics have second derivatives. The famous Newton's equation F equals ma. A is the second derivative of position. So this particular equation here is a common equation. You may have seen it in physics some time ago. This is the acceleration of a mass on a spring. Okay, so this is the force, and here's mass, and there's acceleration. Force equals mass times acceleration. So why is the force minus kx? I think there's a picture down here, or maybe it's up there. Well, I'll just draw a picture. Suppose I have a spring here, and it's attached to the wall. Now, the more I stretch it, the stronger the force. What this says is that the force is proportional to the length of the stretching. The length of the stretching would be x. So the bigger x is, the stronger the force is. And the force is in a negative direction. So the force is, as I move the mass out this way, the force is pointing back this way. Okay, so this would be changing x. Okay, so as x becomes bigger this way, the force will become bigger, but pointing in the opposite direction. All right, so how do you solve this? This seems quite complicated. You can't really solve this by direct integration. Another important thing about second order equations is that you have what are known as initial conditions. For instance, suppose you have a mass on a spring, and you want and at time t equals 0, you want to specify the conditions of that mass on the spring. Now, if you're holding it, then it's just there. It has a location, and if you're just holding it still, it has a 0 velocity. And those are the initial conditions that are listed here. Now, it's possible to have initial conditions where you're not holding it still. It's possible that initially you've given it a boost and it has a non-zero velocity. But this is an example of initial conditions, common example of initial conditions, that the spring has a initial location, and initially the mass is at rest, you're just letting it go, and you want to see what happens to the mass. Okay. Now what's happened here is he has split the original equation up into two different equations. And these equations have physical significance. First of all, if x is the position, then dx dt, if you remember your physics, that's the velocity. And d squared x dt squared, which is the same as ddt of dx dt, you're taking the second derivative, that's the same thing as the acceleration. Okay? So he's kind of stacked these relationships. He said a is equal to the derivative of velocity with respect to time. Velocity is the derivative of position with respect to time. So we write it this way. Okay, now we actually know what the acceleration is. The acceleration, we had this equation up here. Okay, md squared x dt squared equals minus kx. What does that mean? That's the same thing as saying ma equals minus kx. And that's the same thing as saying a equals minus k over mx. So let's plug this relationship in down here. Okay, so that gives us, instead of a equals dv dt, I'm going to replace a with minus k over m times x, and I'll get dv dt. I wish he hadn't done it this way, but that's the way he did it. dv dt, he's replacing the two sides of this equation. dv dt equals minus k over mx. Okay, so this comes from the physical equation. This is just force is equal to mass times acceleration, or actually in this form it's force over mass is equal to acceleration, right? Acceleration is dv dt, and this is force over mass. Now we're also going to write down the the definition of velocity as dx dt. Right? So what we have here really, if you think about it, is a vector equation. This right-hand side I could write as d dt. Well, I've got a v and I've got an x. And then on the right-hand side I have minus k over mx and v. Now, the neat thing about this is that this is now a first-order vector equation. Okay? Now, first order is good because actually I can use the very same Euler method to solve this. I just extend my scalar equation to vector forms. And we're very used to doing that in Octave. you know that if you do dot star, that does multiplication with vectors. So it's easy to convert scalar equations to vector equations. Right? So that's what we're actually going to be doing when we implement the Euler's method for this system. I do also want to mention that the way that this equation is written, it's not really the best. Usually we would write the x first and the v second. So we'd write it this way: d dt of x and v is equal to v minus kx over m. Okay, but these two are equivalent. This one I've just written the v first and the x second. Here I've written the x first and the v second. All right, so let's go on and find out about how to do this. All right, it looks like he's consistently putting the v first, but we'll just have to go along with him. Okay. All right, so we have the differential equation. This is the equation of motion. Okay. Now we also have the initial conditions. We had an initial condition for the location. And we also have an initial condition for the velocity. Now, I'm sorry to say that this is not really correct. He didn't really do this correctly. Really what he wants is x at t equals 0 is equal to x0, and v at t equals 0 is equal to 0. That's really what he wants. I'm sorry that he did this wrong. You can correct in your own paper. All right. So now let's do the analogy of Euler's method. Now, when we had Euler's method, we did x1 equals x naught plus delta t times dx dt, and this is with a vertical bar evaluated at 0. This should be a vertical bar evaluated at 0. Okay. Now, what he's just doing is saying, okay, the same thing we did with x, now we're going to do with the vector x v. I could write this as vx1 equals v0 x0 plus delta t times dv dt dx dt evaluated at 0. Right? So that's really all that he's doing. Very same form of what we had for the first Euler. Now we're going to do it for a vector. All there is to it. Okay? So what he's doing here is simply plugging in the values for the derivatives. Now he's actually doing two things. Instead of going from 0 to 1, he's going from n to n plus 1. Okay, because we're always going from the previous time step to the next time step. But here he's just replacing, here's my value of the acceleration, that replaces dv dt. And here's my value of the velocity, that replaces dx dt. All right, so it's just a simple replacement, very much like the Euler equation that we had with first order scalar. Right. Now here he actually shows some simulations. It shows that the Euler method really is not very good. It should be oscillating back and forth, but here the Euler method it's growing and growing and growing. So Euler method really is not a very good method. It's good for introduction, good for theory, but it's not a very good method. Okay, now here he's writing in vector form. He writes it with this bar in between. I think that's very confusing. You should just take out the bar and forget that the bar is there. Okay. Now he finally changed the order and put the x first and the v second, which is what he should have done in the first place. But remember, I told you that it doesn't matter which order you write the components in as long as you're consistent. Okay. All right, now here he's writing it this way. This y represents a vector. That's the vector at n plus 1. That y represents that. This y represents this one, and this dy dt represents the derivative here. Okay. Now here he's being a little bit sloppy. Instead of minus k there and minus x there, that should be minus kx over m. I guess he's just assuming that k and m are 1. Okay. All right, so now let's look at the program that he uses to do this. Now actually this program is very similar to the original Euler program that we used for the first order scalar case. First he sets up the initial conditions, number of steps, then he sets up a loop, and here's the place where he defines the derivative, and here's where we have the time step, just like in the scalar first order case. Increment the time and then do the plot. Okay. So he says 1.7 is nearly the same as 1.2. All right, so you can compare the two. The only difference is that he's doing, instead of one equation, he's doing two. He really could have done this in a single equation. I'm not sure why he didn't. You could write this as a single vector equation. You could write this as a single vector equation. I guess he's trying to point out the analogy with 1.2. So this is really inefficient method of doing this. You don't really have to write out this program because there will be better programs later on. Actually, the better program is right here. And this program is analogous to 1.6, which was the Euler method for first order scalar. This is now for a vector Euler solver. Similar organization. In this case, t is a vector of times. So that's going to be okay, and notice that t is a column vector the way he's defined it. So he's putting all of his data in columns, which is good. Then data is actually going to be a n by 2. And in this column is going to be x, and in this column is going to be v. And this is going to be at t equals 0. This is going to be at t equal dt. It's going to be at t equal 2 dt, and so on. So the different rows are going to give you x and v at different times. And this is good because it makes it easy to plot when it's organized this way. Okay. All right, so then the rest of it is set up like the previous. We start out with initial time and get a number of steps. Set the time vector. We're going to fill that with times. And then the data is going to be, here it says n steps and length of y. Now, from what we have so far, y just has 2 components. But in fact, you can do any number of vector components. So that's a nice thing about this. This can solve vector equations where the vectors are any length. Okay, so here I said it's n by 2. Here it's actually n steps pi the length of y, where you could have x, v, and several other variables as well. Right? So he's starting out, the first row is going to be the initial conditions. And here he's taking y prime. The prime means transpose. So it looks like he gave the initial conditions as a column vector, and he wants to put that in the first row of his data table. Okay. Now we see some very familiar statements. This is the derivative. This is evaluating this derivative's function at the current time with the current value of y. You increment y according to the Euler formula. So this is the Euler formula. This is the derivative. And here's the increment the time. And here's you're storing the time. And here you're storing the function. Okay. Again, this routine computes y as a column, and it's changing the column into a row. Okay. Now, to get this function, you need to define functions, and these are vector functions. And this derivative function it implements the function we had before. Remember, our system was dx dt is equal to v, and then you had dv dt is equal to minus k over m x. It looks like he's choosing k over m equal to 1, and that's where he's getting this. So this is the second equation, this is the first equation. Okay. Now here's a sample invocation of the function. This gives you the results. Very simple. Here you have your initial conditions, and here you have your time step, that's dt, and here's your final time, and this is the function that contains the derivatives. Okay. Once you have that, t is a column vector. Then the first column of y, this is going to be the x vector, and the second column of y is the v vector. Okay, so you notice that he plotted both the x vector and the v vector. Now he didn't do this very well. He should have put hold on. This is just going to erase the first one and plot the second one. Okay. Right now. All right. All right, so here we have the function, and he's doing this to keep track of which column is the x column, which column is the v column. You can do that or not. You can also do that in your comments, so that's fun. So we have the general idea. All right, now the next method we're going to do is the midpoint method, and this one is a more accurate method than Euler's method. And he gives a derivation based on Taylor series. I'm going to give a little more intuitive definition. Consider a function. See if I can draw this. And it curves up like this. Okay. And let's say this is at time 0, and let's say this is at time delta t. Now, what does Euler's method do? Euler's method says you start here, and I can call that y0 or y of 0. And then to try to estimate here y of delta t, the height here is y of delta t, what do? You take the derivative. Okay, this here is going to be y of 0 plus delta t times dy dt evaluated at t equals 0. And that's Euler's method. You take the tangent line, continue it out to delta t, and that's your estimate of y of delta t. Now you can see that if you have considerable curvature, that it's not a very good approximation. A better approximation would be if you knew the derivative here, if you knew the slope here. Now the slope here is a much better approximation of the slope from y of 0 to y of delta t. So what you'd rather do is replace with y of 0 plus delta t. What you'd like to do is take dy dt at t equals delta t over 2. Because the slope at the midpoint is a much better approximation to the actual slope between y of 0 and y of delta t. Unfortunately, you don't know the derivative at the midpoint. However, you can approximate it. The reason you don't know the derivative is you don't know where the function is. But you can approximate the function. All right, so that's what's going on down here. And let's illustrate this approximation method with an example. Okay. So let's consider the equation dy dt equals minus y. And he's using a large time step to illustrate the method. All right, so we'll have initial conditions y t equals 0 equals 1. So let's just draw it up here. Okay, so you're starting at 1 here. And this, of course, this is t equals 0. Here's t going out this way. Now what this says is if dy dt equals minus y, and y is equal to 1, that means the initial slope is going to be minus 1. Okay. Now we happen to know that this function, the solution is e to the minus y, so the way the function actually goes is something like that. So it's not a very good approximation. So what we're going to do is we're going to, instead of going out delta t, which is here, we're going to just go out delta t over 2. That will take us out here. And then we'll use this as our approximation for y. And then we'll try to evaluate the derivative for the function corresponding to this one. Okay, so how does this work? If I use the equation here, yn plus 1 equals yn plus delta t dy dt. I'm sorry, here I'm going to do this one here. Yn plus 1/2, this should be approximately equal to yn plus delta t over 2 dy and dt. Okay. Now when I'm starting out, my dy dt is going to be negative 1. Okay. So in that case, I'm going to have yn, which is 1, minus delta t over 2. This minus comes from the minus 1 here. All right. So that gives me my new value, my estimate of yn plus 1. And I'm going to use this estimate to estimate the slope. What was this value? This was equal to minus yn plus 1/2. That's how I got this estimate. And I'm going to use this value as the derivative rather than the derivative that comes from the initial value. It's a better value of the derivative. Okay. If I do that as my derivative, unfortunately this is not correct. This should be a minus here. And then you get a much better value. Notice actually if you expand this out, this becomes 1 minus delta t plus delta t squared over 2, which is actually e to the minus delta t, accurate to, the Taylor series is accurate to second order. The first three terms are correct. Okay, so again, the equations that are being implemented are right here. In order to get dy dt n plus 1/2 in approximation, you need y n plus 1/2. You approximate y n plus 1/2 using Euler's method, and then you use that approximation to approximate your derivative at n plus 1/2. So 2 steps, Euler's method for half a step, then use the result to get the derivative in a second Euler step. Okay. And you can see what he's doing here. This is a schematic of what he's doing. He starts out this way, then he stalls Euler for half a step. This gives his new function value of y. Assuming this function, he finds the corresponding slope. Okay. And he uses this slope in a revised Euler step. Okay, so that's how he's working this. Okay. And you can read this caption to catch that. Now this program implements this method. So let's go through and see how this works. Okay. Notice it's set up as a function very similar to the Euler solver, only he calls it midpoint solver. This contains all the information, the initial conditions, the time step, the final time, and the function that contains the derivative. All of this is exactly the same. Initial time, number of steps, the time vector, and the data vector. Okay. All right, so here we start out. The first entry in our time vector is going to be the initial time. The first row in our data vector is going to be the initial conditions. The prime means you take the transpose. Okay, and here we do our steps. All right, so what do? First, we find the derivative at n. We use that to estimate the halfway point. The YH is for halfway, so we're taking Euler's step to midpoint. All right. All right, now here, unfortunately, there's another mistake. This shouldn't be time and y. This time should be time plus dt over 2. Because now we're looking at the midpoint. Did I write dt? No, okay, that's, and this y should not be y. This should be yh. Okay, because I'm using the halfway information to get my new derivative. So there's some mistakes there. These two are not correct. We need to change it to this. Right? So then you take y equals y plus dy times dt, because this is our new estimate of the derivative. Increment the time, store the new time, store the new data, and end. Okay? Not that much more complicated than the Euler method. Okay, but here you see the procedure. You go halfway, use that halfway to estimate your derivative, then use that derivative to carry the Euler step. Now what this shows, and we'll talk about this more in class, is that the error has the same behavior as delta t squared. And what that means, as he says here, that if you divide the time step by 2, you bring the error down by a factor of 4. Okay, so that means you get smaller time steps, you rapidly get increasing accuracy. Now this seems really great, but it's nothing compared to what we'll see later on. And actually it's what we'll see right here. This Runge-Kutta method is really quite common. It's used in engineering quite a bit. And it looks sort of complicated, but it's very similar to the midpoint idea. Instead of the midpoint, you're taking several intermediate points. Okay, so and now we're not going to explain how this equation comes about, but you do need to know how this becomes implemented. Okay, so you start with Tn Fn, and you want to go to Tn plus 1 and Yn plus 1. What did I say? Tn Fn? I meant Tn Yn. Okay, so you start with Tn Yn, you want to go to Tn plus 1, Yn plus 1. Okay, so first of all, you take a full time step. Okay, then here you take another intermediate value. Use that to get another intermediate value, use that to get another intermediate value, and then your final estimate for the next y is the previous y, or the current y, plus some average of these intermediate values. Okay, so to implement this, it's just a matter of doing these equations in MATLAB or Octave. All right, and that's what you have here in this program. Just see how these equations carry over here. The K1, well, all this stuff you should be familiar with. The K1, you take the dt, you're taking the derivative function at time in the current y. Now to find K2, you're taking the derivative function at time plus dt over 2 and the current y plus K1 over 2. And that's what you have here, time plus dt over 2, current y plus K1 over 2. For K3, similar. You're taking dt, I don't know if we can show both of them on the same page, but this equation for K3 corresponds exactly to this equation here. This equation for K4 corresponds to the K4 up there. Here you're taking the average, just continue on. So it's variations on a theme, really not that much different from midpoint method, but much, much more accurate. Okay, and I think I'll stop here for now, and we'll do more stuff in class.